Hello, dear students. I'm Dr. Rajkumari, Assistant Professor in Physics in Government Postgraduate College, Ambala, Kent. I will cover nuclear physics of BSc fifth semester, and today I will start with Unit 1, and my topics will be the origin of nuclear physics and nuclear composition. I hope you all will understand and enjoy my lecture. Let us start with the lecture.
An atom is a building block of every matter in this universe, and its structure was first successfully explained by J. Thomson in his model, which is also known as plum pudding model. According to this model, an atom consists of equal amount of positive and negative charges, keeping atom as a whole neutral. The positive charges, they are uniformly distributed within the spherical volume of the atom, and the electrons are embedded in it like plums or raisins embedded in a pudding. At that time, emission of electrons by the atom were taken as a very strong evidence for the existence of electrons inside the atoms. Many efforts were made in this direction to find the arrangement of electrons and positive charges inside the atom. By that time, there was no evidence of existence of nucleus inside an atom. As far as the structure of atom was concerned, the only thing known at the time was negatively charged electrons and positive charges. In 1911, Ernest Rutherford, with his co-workers Hans Geiger and Ernest Marsden, performed an experiment which is known in the history of nuclear physics as Rutherford alpha scattering experiment. In this experiment, a radioactive source of alpha particle was kept in a lead box with a narrow opening to get a collimated beam of alpha particles. This collimated beam of alpha particle was made to strike a thin gold foil, which resulted in scattering of the alpha particles in different directions. Before coming to the observation of Rutherford scattering experiment, let us take one example. One morning, a large number of students reached at the gate of the college. After entering the college, the students had many options. Maximum number of students, they went straight to their classes. Few students, they moved toward library or canteen, and very few, nearly 1 in 1,000, they decided to go back to his residence. Similar is the case with Rutherford scattering experiment. So let us discuss the observation of Rutherford scattering experiment. We can see in this picture also. From the first observation, most of the alpha particle they pass straight through the gold foil without scattering. From this, it was concluded that most of the space in the atom is empty. The second observation was some of the alpha particles were scattered by gold foil through small angles. The explanation for this was since alpha particles they are positively charged particles, so there might be something which is positively charged inside the atom which deviate these alpha particles through small angles, and that positive charge in an atom is not uniformly distributed, rather it is concentrated in a very small volume at the center. The third observation was very few alpha particles are deflected back, that is they were scattered through an angle of 180 degree. It means that these alpha particles they directly hit the positively charged region which is very small and dense as compared to the total volume of an atom. That is why such kind of alpha particles with large angle scatterings are very small. So Rutherford alpha scattering experiment lead to following conclusions. The positively charged region as well as the most of the mass of the atom is concentrated in the very small volume at the center, and Rutherford named this region as the nucleus. The size of nucleus is very small and also the nucleus is very dense. This central nucleus is surrounded by cloud of electrons, and the total charge on these electrons is same as the positive charge on the nucleus, so that the atom as a whole is electrically neutral. This discovery of positive and massive region inside the atom, which was named nucleus, it opened door for new branch of physics called nuclear physics. So this is how the nuclear physics comes into picture. Rutherford alpha scattering experiment revealed many facts about size and density of the nucleus. Now the interest arises in the composition of the nucleus. What are the building blocks of a nucleus? What are the constituents of a nucleus? In this direction, several theories were proposed about the nuclear composition. Natural radioactivity suggested that nucleus is capable of emitting many several particles like alpha, beta, and gamma rays. Cosmic rays studies predicted the existence of meson inside the nucleus. So all these findings motivated the people working in the field to explore nucleus for its constituents. And the two dominating theories in this regard are proton-electron theory and proton-neutron theory. First, we will discuss the proton-electron theory. According to this theory, protons and electrons were considered as the building block of the nucleus. Neutron was not discovered at the time. According to this theory, some electrons were considered to be inside the nucleus and some outside the nucleus. And the total number of electrons and protons in an atom were considered equal in order to keep atom neutral. Here we can explain it with the help of an example. Let us consider nitrogen atom. According to this theory, nitrogen atom has 14 protons and 14 electrons, so as to keep the nitrogen atom neutral. All 14 protons exist inside the nucleus. 7 electrons out of the total 14 electrons, they exist inside the nucleus, and the remaining 7 electrons are outside the nucleus. There were few experimental facts observed which support this proton-electron theory. The first point was electrons were emitted by radioactive nuclei during beta decay. This supports the existence of electron inside the nucleus, on which basis this proton-electron theory was proposed. The second was, from the mass spectrum data, the masses of the different nuclei were found to be the whole number multiple of mass of the hydrogen nucleus, which is also known as proton. This observed fact confirmed the presence of proton inside the atom. The proton-electron theory was discarded due to many reasons. The first reason was wave mechanics considerations. If electron is confined inside the nucleus, then the uncertainty its position, that is delta x, it should be equal to the radius of the nucleus, and which is equal to 2 Fermi meter. According to the Heisenberg uncertainty principle, if uncertainty in momentum is maximum, then uncertainty in the position will be minimum, and vice versa. So using this Heisenberg uncertainty relation, delta P into delta X is equal to h bar, and which is equal to h upon 2 pi, where this delta P is uncertainty in the momentum, delta X is uncertainty in position, and H is Planck's constant. This implies that delta P is equal to h bar upon delta X. Using the value of the Planck constant and by taking delta X equals to 2 Fermi meter, the value of delta P, it comes out to be 0.527 10 raised to power minus 20 joule second per meter. The magnitude of the momentum of the electron in the nucleus, it must be at least of the order of delta P. So we have considered P is nearly equal to delta P. Using the equation for energy of the electron emitted from the nucleus, that is E is equal to square root P square C square plus m naught square C4, where P is the linear momentum, this C is the velocity of light, m naught is the mass of the electron. And also by taking the rest mass of the electron is equal to 0.511 mega electron volt, the energy of the electron emitted from the nucleus, it comes out to be 10 mega electron volt. What does this imply? This implies that if electron exists inside the nucleus, the energy of the emitted electron must be of the order of 10 mega electron volt. However, the electron emitted during beta decay have energy only in the range of 3 to 4 mega electron volt. So this implies that electron cannot exist inside the nucleus, and this was a major setback to the proton-electron theory, which was based upon the fact that electron exists inside the nucleus. The second point which was responsible for the failure of the proton-electron theory was nuclear spin. The spin of a nucleus is due to the spin of its constituent particles. And according to proton-electron theory, the nucleus is composed of protons and electrons. Let us take example of nitrogen nucleus. The nitrogen nucleus have 14 protons. Each proton has spin half and 7 electron, again each electron with spin half. So in total, the nitrogen nucleus has 21 particles. And in this way, the nitrogen nucleus will have half integral spin. However, the experimental data predicted that the nitrogen nucleus has integral spin. So in this way, the proton-electron theory was not able to explain the nuclear spin. The next point, which was responsible for the failure of proton-electron theory, was the nuclear magnetic moment. Due to its charge and angular momentum or spin, the nucleus has a magnetic moment associated with it, which is called nuclear magnetic moment. Since nucleus consists of protons and electrons according to this theory, and also the magnetic moment of electron is 2000 times the magnetic moment of protons. So if electron exists inside the nucleus, the magnetic moment of the nucleus, it should be very high. However, experimental data predicted that magnetic moment of the nucleus is much smaller than the magnetic moment of the electron. In this way, proton-electron theory was not able to explain the nuclear magnetic moment. The last factor which was responsible for the failure of proton-electron theory was the dual nature of electron. According to this theory, some of the electrons they exist inside the nucleus and the other electrons they exist outside the nucleus, which means that the electrons they exist in two different environments which exhibit their dual role and which is very difficult to understand. So due to all these reasons, the proton-electron theory or hypothesis was discarded, and the failure of this proton-electron theory and the discovery of neutron by James Chadwick in 1932 leads to the another theory which is known as proton-neutron theory. The discovery of neutron by James Chadwick in 1932 led Heisenberg to propose proton-neutron theory. According to this theory, a nucleus has Z number of protons and A minus Z number of neutrons inside it, where Z is called the atomic number and A is called the mass number, which is equal to the number of nucleons inside the nucleus. The protons and neutrons, they are collectively known as nucleons. Also, according to this theory, Z electrons, they are revolving around the nucleus. Since number of protons which are positively charged are equal to number of electrons which are negatively charged, so atom as a whole is electrically neutral. And since neutron is neutral, so the nucleus is positively charged due to the presence of protons inside it. This theory was successful in explaining the objections which were faced by the proton-electron theory. In this theory, the electrons are no longer the constituent of the nucleus. The existence of neutrons inside the nucleus obey the uncertainty principle. This theory successfully explained the concept of nuclear spin. According to this theory, if a nucleus has a number of nucleons, then the nuclear spin will be integral multiple of h bar if A is even and half integral multiple of h bar if A is odd. Let us explain it with example of nitrogen atom. According to proton-neutron theory, the nitrogen nucleus has 7 protons and 7 neutrons inside it, and the 7 electrons they are revolving around the nitrogen nucleus. In this way, the nitrogen nucleus has integral spin. And this is also supported by the experimental observations. The proton-neutron theory also explained the nuclear magnetic moment. The nuclear magnetic moment of a nucleus is due to its constituents, which are protons and neutrons. The nuclear magnetic moment is now accordance with experimental data. The electron emission during the beta decay is also explained by the proton-neutron theory. According to this theory, the electron does not pre-exist in the nucleus, but it is formed during the transformation reaction. That is, when a neutron inside the nucleus it changes to proton, then the electron is emitted with an antineutrino. This electron is emitted during the beta decay. Now the protons and the neutrons are bound together inside the nucleus due to the exchange of particles which are known as pi meson. In this way, existence of pi mesons, also called pions, as predicted by the cosmic ray study, is also explained by the proton-neutron theory. Using the wave mechanical consideration, if neutron is confined inside the nucleus, then the uncertainty in its position, that is delta x, is equal to the radius of the nucleus, that is 2 Fermi meter. Using the Heisenberg uncertainty relation, that is delta p into delta x is equal to h bar, where delta p is the uncertainty in the momentum, delta x is the uncertainty in the position, and this h is called the Planck's constant. By taking delta p equals to p and by taking the mass of the neutron or proton equals to 1.67 10 to the power minus 27 kg, the total energy of the neutron or protons it comes out to be 1000 mega electron volt. This value is slightly greater than the rest energy of protons or neutrons, which is actually nearly equal to 938 MeV. Thus, it is possible for the neutron to be contained in the nucleus. The next comes the statistics. Protons and neutrons, being the spin half particles, they obey Fermi-Dirac statistics. Since mass number is the sum of number of protons and number of neutrons, so if a nucleus has even mass number, then it will have even number of particles, and thus it will have the integral spin. Due to this, the nucleus with even A will obey Bose-Einstein statistics. And if the nucleus with if the A is odd, that is the nucleus had odd number of particles, then the spin of the nucleus will be half integral, and therefore it will obey Fermi-Dirac statistics. And this fact is strongly agree with the experimental result. In this way, the proton-neutron theory successfully explained all the objections faced by the proton-electron theory. Due to this reason, the proton-neutron theory is the most acceptable theory for nuclear composition and is still the accepted one. Let us practice few numericals. The first numerical is compute the energy of 1 AMU in mega electron volt. 1 AMU is actually at the atomic mass unit. From the Einstein relation E is equal to mc square, the energy and mass are interconvertible. That is, energy can be converted to mass and mass can be converted to energy. So in this numerical, we have to find the energy corresponding to the one atomic mass unit. Using the value of c as the velocity of light, 3 in 10 per 8 meter per second, and one atomic mass unit is equal to 1.67 10 minus 27 kg. We can find the value of E in joules. Now we can convert joules into electron volt by using this relation, that is 1 mega electron volt is equal to 1.6 10 per minus 13 joules. In this way, we can find the value of energy in MeV. So we find that the energy of 1 AMU is equal to 931 mega electron volt. Now comes to the second numerical. The second numerical is find the density of C612 nucleus. We have been given a carbon nucleus with 6 protons and 6 neutrons, so that the mass number is 12. Now we know that the formula for density is equal to mass upon volume. Here we have to find the density of the nucleus, which is equal to mass of the nucleus divided by the volume of the nucleus. The mass of the nucleus is mass of a nucleon into the total number of nucleons inside the nucleus divided by the volume of nucleus, which is equal to 4/3 pi r cube, because we consider the nucleus to be a sphere and the volume of sphere is 4/3 pi r cube. Now mass of a nucleon, since a nucleon can be a neutron or proton, so we have taken the mass of a nucleon to be 1.67 10 to the minus 27 kg, and the total number of nucleon is actually the mass number, so we have taken it as A. By using the relation for nuclear size, that is R is equal to R naught A raised to power 1 by 3, where this R naught is equal to 1.4 fermi-meter. By using this value, we find the density of the nucleus. It comes out to be 10 raised to power 17 kilogram per meter cube. So also from the observations of Rutherford alpha scattering experiment, we found that the nucleus is very dense. So here we can confirm from these calculations, because here also this factor is very high, which confirms the high density of the nucleus. Now the numerical number 3. This numerical is actually based on the validity of proton-electron theory and the proton-neutron theory. The statement of the numerical is: the measured nuclear spin and symmetry character of nitrogen with Z is equal to 7 and A is equal to 14 are 1 and symmetric. we have been given a nitrogen nucleus with Z atomic number 7 and mass number 14. And the measured value of nuclear spin is 1, and the character of this nitrogen nucleus is symmetric. Now we have to prove that these measured value will disagree if we assume that the nuclei contain A proton, means 14 protons, and A minus Z means 7 electrons, means protons electron theory. So here we will apply proton electron theory. So let us take case 1. That is proton electron theory. If the nucleus contain 14 protons and 7 electrons, then it will contain odd number of particles. 14 plus 7 is equal to 21. We know that protons and electrons are half spin particles. So since the total number of particles are odd, so the total spin will be half integral. But the measured nuclear spin is 1, which is integral. So this assumption disagree with the measured value. Let us check for the symmetry also. The symmetry of a nucleus is given by S equals to minus 1 divided by total number of particles, which in this case are odd. So S comes out to be minus 1. That is antisymmetric. However, according to the measurement, the nitrogen nucleus is symmetric. So these assumption of the proton electron theory, they are in disagreement with the measurement. So let us check for the proton neutron theory also. Now if the nucleus contains 7 neutrons and 7 protons, since we have Z is equal to 7, so we will have 7 protons, and since mass number is 14, so we will have 7 neutrons. So in this case, the total number of the particle in the nucleus will be even, since these two are the spin half particles. So the total spin of this nucleus will be integral. And also, since total number of particles is even, this S will comes out to be positive, that is symmetric. So using the proton neutron theory, our results are in agreement with the measurements. So in this way, we prove that the measured values, they disagree with the assumption that nuclei contain A protons and A minus Z electrons. That is the proton electron theory. So this is all about this lecture. I hope you understand and enjoy my lecture. Thank you very much.